Imagine you could see the invisible, not with your eyes, but with your mind. You'd see the Earth creating a deep dent in the fabric of the universe, like a bowling ball on a trampoline. You'd see the sun warping space so dramatically that our entire solar system rolls along its curves. You'd see time itself stretching and compressing, flowing faster at the top of mountains and slower near massive objects. You'd see that what we call empty space isn't empty at all. It's a living, breathing entity, bending, rippling, even singing as massive objects collide across the cosmos. This isn't science fiction. This is reality. In 1915, one man saw this invisible universe with nothing but the power of his mind. Albert Einstein discovered that space and time aren't the rigid framework we thought they were. They're woven together into a single fabric that can be twisted, stretched, and torn. And once you understand this, everything changes. The way planets orbit stars, the way light bends through the universe, even the possibility of traveling through time itself. It all makes sense in a completely new way. This is the story of one of the greatest discoveries in the history of science. The story of how a patent clerk in Switzerland overturned everything we thought we knew about reality. The story of spacetime, the foundation of all existence. Hello and welcome to Space and Time. Today, we'll explore the deepest secret of the universe. We'll journey from ancient ideas about gravity through Newton's revolution to Einstein's genius breakthrough. And along that journey, we'll witness how humanity's entire understanding of reality changed forever. Our journey begins with a simple question: why do things fall down? For thousands of years, humans knew that things fall to the ground, but no one truly understood why. Aristotle, the great philosopher of ancient Greece, believed that objects fell because they were seeking their natural place. Earth belongs to earth, water belongs to water, and air belongs to air. According to him, this was the nature of the universe, a predetermined order. This theory persisted for nearly 2,000 years, until a man in 17th century England began asking different questions. In 1666, London was gripped by the bubonic plague. Isaac Newton, then just 23 years old, left Cambridge and returned to his family farm in Woolsthorpe. It was there, according to legend, that he witnessed an apple fall from a tree to the ground. But what made Newton different wasn't seeing the apple fall. Millions had seen that. What was special was the question he asked next. Newton looked up at the moon in the sky and wondered, if gravity pulls the apple down to Earth, does it also pull the moon down? And if so, why doesn't the moon fall like the apple? This was the moment of genius. Newton realized that the moon actually is falling, but in a special way. It's moving sideways fast enough that, as it falls toward Earth, it keeps missing us, creating a circular orbit. It took Newton nearly 2 more decades to perfect this idea. In 1687, he published Principia Mathematica, perhaps the most important scientific book ever written. In it, Newton made a bold claim: every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It sounds complex, but the meaning is simple and profound. The apple attracts Earth, just as Earth attracts the apple. You attract the sun, just as the sun attracts you. Gravity isn't Earth's privilege, it's a universal property of all matter in the cosmos. Newton's formula was simple yet stunningly powerful. It explained planetary motion, ocean tides, even the orbits of comets. For the first time in history, humans could accurately predict the movement of celestial bodies. And then in 1846, Newton's formula accomplished something extraordinary. Astronomers noticed that Uranus wasn't moving quite as predicted. Its orbit kept deviating slightly, as if something invisible was tugging at it. Using Newton's mathematics, French mathematician Urbain Le Verrier calculated that there must be an unknown planet hiding out there somewhere. He predicted its exact location, and when telescopes pointed to those coordinates, they found Neptune, a new planet, discovered purely through the power of mathematics. This was Newton's greatest triumph. For over 200 years, His formula reigned supreme. It was so accurate that people believed we had completely understood gravity. But there was a problem. Even Newton knew something was missing. He could describe how gravity worked, but couldn't explain why it worked. How could two objects millions of miles apart know to attract each other? How does this force transmit through space? In a letter to a friend, Newton admitted that gravity should act across vast distances without any intermediary medium is to me so great an absurdity that I believe no man who has competence in philosophical matters can ever fall into it. Newton had described gravity perfectly, but he didn't understand what it was. The answer would come over 200 years later from a young man at a patent office in Switzerland. Entering the 20th century, physics seemed almost complete. Newton's laws explained motion. Maxwell's equations explained electromagnetism. Many scientists believed all the big questions had been answered. But small cracks were beginning to appear, strange anomalies that no one could explain. One of these mysteries involved the planet closest to the Sun, Mercury. Since the mid-19th century, astronomers had observed something odd. Mercury's orbit wasn't completely stable. It had an elliptical shape like all other planets, but this ellipse was slowly rotating around the Sun, a phenomenon called perihelion precession. Newton's laws predicted some precession due to the influence of other planets. But when carefully calculated, a small piece was missing, about 43 arcseconds per century. It doesn't sound like much, but with the precision of astronomy, this was an unacceptable discrepancy. Some scientists even proposed there must be an undiscovered planet closer to the Sun than Mercury, naming it Vulcan. But there was no Vulcan. The problem wasn't a missing planet. The problem was with Newton's theory of gravity itself. In 1905, a 26-year-old man named Albert Einstein was working at the patent office in Bern. He had graduated from university, but couldn't find an academic position. So by day, he evaluated patent applications, and in his spare time, he thought about the universe. That year, Einstein published 4 papers that would change physics forever. One introduced special relativity, a theory about space and time at high speeds. But Einstein knew his theory wasn't complete. It worked well for constant velocity, but couldn't explain acceleration. And more importantly, it couldn't explain gravity. A year later, in 1907, Einstein was sitting at his desk when a thought struck him, what he later called the happiest thought of my life. He imagined a painter falling from a roof. While falling, the person wouldn't feel their own weight. If they dropped a wrench, it would fall at the same rate and appear to float beside them. For the painter, in that moment, gravity seemed to disappear. But how could this be? How could gravity both exist and not exist depending on your perspective? Einstein realized something profound. There's no way to distinguish between free falling in a gravitational field and floating in deep space. Both experiences are identical. And from this, he drew a breakthrough conclusion. Gravity isn't a pulling force. It's a property of space and time itself. But turning this idea into a complete mathematical theory was monumental. Einstein spent the next 8 years wrestling with the most complex mathematics he had ever encountered. He had to learn tensor calculus, a branch most physicists weren't familiar with. He made mistakes, hit dead ends, and nearly gave up many times. He wrote to a friend, "I have never labored over anything as much as this. What I have accomplished fills me with deep respect for mathematics, the subtler parts of which I had until now considered mere luxury." Finally, in November 1915, Einstein completed his theory. He presented it in 4 lectures at the Prussian Academy of Sciences in Berlin. General relativity, that's what he called it, was one of humanity's greatest intellectual achievements. Einstein proposed that space and time are not fixed stages where events occur. They are dynamic entities that can be bent, stretched, and deformed by mass and energy. Gravity, according to Einstein, is not a force. It's the shape of space-time. Planets aren't pulled by the sun. Instead, the sun curves space-time around it. and planets simply follow the straightest possible path through that curved space. Right after completing the theory, Einstein applied it to Mercury's orbit problem. The result? His theory perfectly explained those mysterious 43 arcseconds, the discrepancy Newton's laws couldn't account for. When he realized this, Einstein later recounted feeling as if his heart would burst. He knew he had touched upon a deep truth about the universe, but the scientific community needed more than a retroactive explanation. They needed a new prediction, something Newton's theory couldn't predict, but Einstein's could. Einstein calculated that light from distant stars would be bent when passing near the sun, and the exact amount would differ from Newton's prediction. The problem? To observe this, you needed a total solar eclipse, and the world was in World War I. It wasn't until 1919 that British astronomer Arthur Eddington organized an expedition to Principe Island to observe an eclipse. When the photographs were analyzed, the result was clear. Light was bent exactly as Einstein predicted. News spread around the world. Overnight, Einstein became the most famous person on the planet. Headlines proclaimed, "Revolution in Science, Newtonian Ideas Overthrown." Einstein hadn't just overthrown Newton, he had forever changed how we understand reality. Throughout human history, we've always treated space and time as two completely separate things. Space is where everything exists. Time is the flow from past to future. Newton believed time was absolute. A second on Earth equals a second anywhere in the universe. Time flows uniformly everywhere, like an eternal river. But Einstein proved this was completely wrong. To understand why, let's do Einstein's famous thought experiment. Imagine you're standing beside a railroad track. A train speeds past. Just as it passes, two lightning bolts strike. One ahead of the train, one behind it, and you're standing exactly midway between them. For you, standing still, light from both bolts travels the same distance to reach your eyes. Since light always travels at the same speed, you see both lightning bolts strike simultaneously. That's the truth for you. But now consider someone sitting on the train, in the middle. While light from both bolts travels toward them, the train is moving toward the front bolt and away from the rear bolt. Light from the front bolt reaches them first. Light from the rear bolt arrives later. For the person on the train, the front lightning struck before the rear lightning. That's also the truth for them. So, what is the truth? Did the two bolts strike simultaneously or not? The strange answer is, both are correct. There is no absolute answer. Simultaneity depends on your perspective. This isn't just philosophy. In 1971, physicists Joseph Haffel and Richard Keating placed extremely precise atomic clocks on commercial airliners and flew them around the world. When the clocks returned, they were compared with identical clocks that remained on the ground. The result? The flying clocks ran slower, only a few billionths of a second, but measurable. Time really had passed more slowly for the moving clocks. This effect is so real we account for it every day. GPS satellites orbit Earth at high speeds, so their clocks run slower than ground clocks. Without correcting for this, your GPS would be off by kilometers in minutes. And here's the magical part. It's not just motion that slows time. Gravity does too. In 1960, physicists Robert Pound and Glenn Rebka conducted an experiment at Harvard University, using the Musbauer effect to measure the frequency shift of gamma rays between two heights 22.5 meters apart in the Jefferson Tower. The results showed that gamma rays at the higher position, where gravity is slightly weaker, had a slightly higher frequency than those at the lower position. The difference was extremely small, but confirmed the prediction of general relativity regarding gravitational time dilation. What Einstein realized was, space and time cannot be separated. They are two sides of the same coin. When you move through space, you affect how time flows. When mass curves space, it also curves time. We needed a new word for this unified concept, spacetime, a four-dimensional fabric upon which the universe is woven. Here's one final strange truth. Even when you think you're standing still, you're actually moving through spacetime at the speed of light. Every second that passes, you're moving 1 second into the future through time. That's motion through space-time. When you start moving through space, some of that motion through time gets redirected into motion through space. That's why time slows down when you move faster. Your total speed through space-time is always constant, the speed of light. You can only change how it's distributed between motion through space and motion through time. This is Einstein's revolution. Space and time aren't stages where cosmic events unfold. They are the events themselves. They're dynamic, flexible, and responsive to everything in the universe. Gravity isn't a mysterious force. It's geometry, the shape of space-time itself. A century has passed since Einstein published general relativity. And throughout that time, this theory has been tested thousands of times. Every time, it's been correct. We've observed gravitational lensing, massive galaxies, bending light like cosmic magnifying glasses, allowing us to see objects hidden behind them. We've discovered black holes. In 2019, we captured the first photograph of one, showing precisely the dark ring Einstein predicted a century earlier. And in 2015, 100 years after Einstein completed his theory, we detected gravitational waves, ripples in space-time itself, created when black holes collided billions of light-years away. But understanding space-time doesn't just help us explain the universe. It opens possibilities that previously existed only in science fiction. If space can be curved, could we learn to curve it at will? Could we create warp bubbles in space-time, allowing ships to travel faster than light by compressing space ahead and expanding space behind, as physicist Miguel Alcubierre proposed in 1994? Or could we find or create wormholes, tunnels, through space-time, connecting distant points? Einstein's mathematics says they could exist, but would they be stable? The universe expands faster than light, moving most of it beyond our reach forever. But if we could manipulate space-time, create shortcuts, folds, bubbles, the entire universe becomes accessible again. That's why understanding space-time is the foundation for humanity's future as an interstellar civilization. And then there's time. If space and time truly are one, if we can move through space in any direction, why not move through time? Einstein's relativity doesn't forbid time travel. It describes exactly how travel to the future works. Move fast or stay near strong gravity, and you'll jump forward. Astronauts on the International Space Station have already time-traveled thousandths of a second into the future. But what about the past? Is it possible? Or does the universe have some fundamental rule preventing it? These questions touch the deepest nature of causality, free will, and reality itself. We'll explore them in future episodes. And here's the most miraculous thing. A human being, sitting at a desk with only pen and paper, using only imagination and persistence, discovered this truth about the universe. We've come a long way today, from falling apples to understanding the universe is woven from bendable fabric, from Newton to Einstein, from gravity as a force to gravity as geometry. But our journey has only begun. The universe is vaster than we thought, stranger than we imagined, and more wonderful than our wildest dreams. If you enjoyed this journey through space-time, please give this video a thumbs up and subscribe to Space and Time. And as Einstein once said, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. Until next time, keep looking up and keep questioning.